This is an MRSGS video again. This time with a focus on what I used to call digigraphs. That's like digit graphs. Graphs of, well, numbers based on the sequence of digits, wherein the basically the, well, you have a base for the, base numeral systems, such as base 10, or in binary base 2, and so on. That base can be thought of as a modulus for the sake of modular, systems, for, just to say MRSGSs, modular residue graphing systems. So the base of a numeral system and the modulus of its equivalent MRSGS kind of provide a really neat way to, to graph numbers. Now, I'm not talking about sequences of numbers in that usual sense, but a number by itself, as is represented by a sequence of digits. So, the first thing, of course, that I did was to graph, some rational numbers, being periodic in nature and whatnot. And so, we get these sorts of, for example, 1 over 103, 103 being prime. This is in base 10, and the digits are being graphed over a modulus, therefore, of, mod 10. And so you can see this is only slightly embellished with a slight embossing sort of algorithm. But you can see this is a pretty wonderful and interesting graph that essentially represents the number 1 over 103. In a similar manner, slightly less embellished, we have 1 over 987 base 10. And you can see it repeats this shape over and over again as it repeats its digits in base 10 over and over again on into infinity. And here we have, well, just a repeating of 1, so this is 1/9 in base 10, and you can see that, the 11111 or 0.1111, gives you this rather basic dodecagon. Here we have 2 over 103, so 2 times the 103 that we saw previously, giving a slightly different sequence of digits. Without going into the details of that, we see a rather different shape as well. And this one being less embellished, just the basic framework of the graph itself for the number 2 over 103. Here is 4 over 103. Again, notice a different graph here from the previous one. Just quickly flash back to that. 2 over 103. 4 over 103. So you can see it does matter, these details of the exact digit sequence as far as how they are eventually portrayed or graphed in these MRSGS systems. This again being mod 10 for the base 10 representation of 4 over 103. Now this is just the sequence 110, and we can see that coming up like that, repeated over and over again. And this is the same idea, but in base 5. Yeah, there we go. So there's that. This is in base 5, 110. So you can see it creates this shape. So it's a sequence of digits, 0.110, 110, 110 forever. And here we have in base 10 the digit sequence 0.15911 repeating, and this is a graph of that rational number. And here we have, the sequence 1 or 0.110100 being repeated over and over again. So you put your vinculum bar, as it's called, over these digits here, and they would repeat forever, and you would get this sort of a graph. And here in base 5, we have the same sequence, giving this graph. So this is a rational number, the graph of a rational number, with that repeating digit sequence 0.110100. And again, but with the digit sequence 0.1101001000. I'm reading right off of here. This is in base 5. I will spare you the details of exactly what the significance of the sequence is. Suffice it to say, at the moment, it relates to the primes and their distribution amongst the integers. But moving on. And here we have, in base 10, a number sequence, which is, of course, as soon as you get into this, you're like, oh gosh, what if I just, alternate digits of this or that, and what kind of graph would it give you, and what about the number that is 0.1213141516171819 repeating in base 10? Well, that's what this looks like. That's a graph of that number. And here we have base 10 again, only this time it's sort of this alternating between 1 and 9, and then 2 and 8, 3, 7, and so on. There's a slight divergence from that pattern here with the 6, the 4, 5, 6. Anyways, you can look at that if you'd like. It's palindromic. And anyways, it gives this rather interesting shape as its graph. And I'm not going to read out this rather long rational number digit sequence here, the repeating sequence of digits. But if you were to graph that rational number, right, you would end up with this sort of a graph in base 5. And yeah, rather interesting looking thing. And that's the same sequence without the embellishment. Yes. So you can see that's just the framework right there. Already nice without any embellishment. Okay. And here we have another, okay, what if I do this with this sort of thing? We got 1, 2, 1, 3, 1, 4, and then it continues, but then it palindromically descends from there. So 1, 8, 1, 9, 1, 8, 1, 7, 1, 6, and so on, all the way to 1, 3, 1, 2, and then repeats that over and over again. And this is embossed, so you can see there's a nice sort of artistic flair to it, or more to just emphasize its structure than anything. Nothing that distorts its shape, per se. At any rate, you get this sort of a graph in base 10. That's its framework. Again, already interesting without the embellishment. Yeah. And here we have another sort of sequence of the sort. In this case, we have the 1, 2, 3, 2, 3, 4. Anyways, you can follow that if you'd like. In base 10, giving you this graph of that rational number in base 10. Of course, these are base sensitive in that sense, but that said, you can also change the base if you desire. And of course, we do desire. As to see a number in one base, well, that certainly isn't enough for someone like myself. I like to see that number graphed in, well, a fair number of bases. Anyway, and of course, their respective MRSGS systems. So this is the digits 1146 in base 10, repeated over and over again. So, 0.1146, 1146, 1146. Anyways, we get this sort of a graph there. Now, another way to do this is to first think of a shape, graph that shape, and you'll end up with a digit sequence. And in this case, it's a closed graph that, as the graph goes, it repeats this pattern over and over and over again. And so you can do it backwards like that too, and get, numbers from shapes. So that's fun. And that's just an embellished variation of that. I did this for a present for someone several years ago. This is that same sequence that gave that, sort of crucifix-looking shape, or meta-crucifix, as I'm calling it. But now it's in base 10. Previously, it was not. At any rate, And you can see you get a very different looking shape, and I must say rather nice at the same time. And this is also slightly embellished, it looks like, but otherwise the basic shape is shown. All right, now just permutations of 1, 2, 3 in base 10, taken as a digit sequence that is being graphed, right? So point 1, 2, 3, 1, 3, 2, 2, 1, 3, and so on all the way to 3, 2, 1, and then repeat. So every single permutation of the, digits 1, 2, 3 in lexicographical order, so least to greatest order, taken as a digit sequence that repeats. Anyways, this is in base 10, so over a mod 10 in the MRSGS systems, and you get this rather lovely shape representing that number. And here's a much more complex, sort of number being graphed here. I won't specify the digit sequence, but it's an extension of some of the previous graphs we've seen. This happens to be in base 10. Move along. And well, I guess I might mention that there are sometimes these motifs, graph motifs, that might or might not coincide with the digits that repeat. And then, you get that repeating as a graph, and you have this cyclic graph that, ends up repeating itself also. Okay, and this is that same one without the motif highlighted. And a similar thing here. And here. As well as here, but a little bit embellished. So notice you can also get these more sort of almost curvy looking shapes as opposed to strictly angular looks, depending on the refinement of the base and the sequence itself. And so that's with, rational numbers. And so let's get this one here and go into, I suppose we could say, and that of course led me to think of, well, what about sequences in general? So first it was the digigraphs, actually. And then it was a question of, well, gosh, I wonder what would happen if, say, powers of 2 mod 13, and there it is. What about powers of 2 mod 3, and what about mod 7 and mod 21, and these are those. What about powers of 2 over a modulus of 25? They create this shape. And so on. Of course, I've already done some videos on sequences more generally, as the MRSGSs are good for. It's just that, that first initial sort of, discovery of this method of graphing, kind of the first question was, gosh, one of the first questions, gosh, wonder what numbers would look like after all as they are represented in base numeral systems. They're, more simply than not, sequences of digits, whether they repeat or otherwise, based on whether they're rational or irrational, respectively. At any rate, so those are some sequences, powers of 8 mod 25 there, and you can imagine there's some other wonderful shapes to be seen. So, yes, how about some irrational numbers? After all, once you've seen some rational numbers, you're going to want to see some irrational numbers. And so that was one of the first things I did also. So, I've of course done graphs of, pi and such things, square root of 2, and golden ratio. Those were one of the first things I did, so I'm actually having trouble finding those in the older drives of computers that once were. Here we have 1 over e, so that puts it in between 0 and 1, which is convenient, as we just graph the digits after the decimal point. This is the first 50 digits of that, presuming base 10, if not otherwise specified. This is 1 over the square root of pi, some number of digits of that in base 10. Over here we have 1 over the zeta function of 2. This is the first 314 digits, never minding the math behind all that, unless you are familiar with it already. There is that rather interesting graph there. Here we have 1 over zeta of 2 in the absolute MRSGS system, first 314 digits. Again, assuming base 10 unless otherwise specified. Some rather interesting shapes occurring here. And here's a graph of 1 over e, the first 50 digits, but truncated and then repeated. So it's sort of a rational number approximation of e, accurate to the first 50 digits. All right. And, well, there it is. And, yeah, here's the, okay, first 10,000 primes with digits in base 10, or digits of base 10, over a modulus of 5. So yeah, so that's taken the, prime numbers, such as 2, 3, 5, 7, treating them as a digit sequence, 0.2, 3, 5, 7, 11, so 1, 1, 1, 3, that kind of thing. And you take that over a modulus of 5, and here you are. It's the first 10,000 primes. And here's Euler's constant, or E, right, 2.71828, and so on. This is the first 170,000 digits. It's a sort of close-up, as you can see, trails off the edges of the window of view here. And here's Euler's constant again, only such that it fits in our window. This is still just the first 170,000 digits. And again, different magnification. Just amazing detail here. All right, and again, just another zoom into one of the areas of that same graph of E. And again. And there again. And then square root of pi. This is in base 10. And yeah, clearly as it is repeating here, it's truncation of an unspecified, unfortunately, amount. I didn't specify that in the name of the file, so there we go. At any rate, it's been truncated and repeated. Here we have square root of pi, first 50 digits, so I'm led to believe that's the motif of this graph here, but I won't say that for sure. At any rate, that's just the first 50 digits, not repeated. And there you go. So you can see irrational numbers provide a really very interesting area of exploration for these MRSGSs, or rather MRSGSs provide a very interesting area of exploration for irrational numbers, as well as rational numbers in various base systems that are then thought of as various equivalent moduli, as in the sense of MRSGSs. And so, there's that. And so you think, okay, well, gosh, what else could I do with this? Well, one thing, in base 36, for example, we have the digits 0 through 9. And then, as is often done, we then start with our letters to augment our base from there. So base 12, we would, have the A and the B for our digits as well. And then from there we would have C and D and so on for hexadecimal. And in base 36, we go all the way up to Z and then back to 0 again. And if we do that same thing as we've been doing with the MRSGSs, wherein we have 0 is one direction, 1 is another direction, 2 is another direction. Anyways, you get the idea. We can graph any combination of words and numbers without the punctuation. And, get a, let's say this more legible or readable. You can graph any word, which of course is being understood as a number or a sequence, depending on how you are thinking of it. And so that was another thing I did. In fact, did quite a bit of that. It makes for great presence. So this is the name here. Rose, R-O-S-E, as a sequence of letters, which are understood to be digits that are repeating over and over again in base 36. Here is a name graph, somewhat artistically embellished, of Adrian Marie Beasley, and that's a sequence of letters as far as this graphing system is concerned. Here we have Alexis. I had, as a thing I did as a substitute teacher, I would sometimes treat my students to some name graph sessions once we finished everything we had to do that day. And they get all excited. It's fun to see elementary students getting so excited for, some math art. And so they would, do my name. So anyways, that's one of the names that was done. Very cool. This is the name Emilia. Very cool. And again, this is somewhat, it's embossed a little bit to make it look just that much nicer. This is Emilia with a thicker embossing. This is Blanca Estella Lucas, more artistically rendered here. This is the name Chris. The name Chris in different colors. And Chris in a more monochrome or grayscale. And the same name, but with just more of the skeletal framework. Very cool shape. And here is Dominic, or Domink. Oh, Domink. I guess maybe I misspelled the word, the name. Well, there you go. Don't tell him that. Dominic. Okay, no, that was the right name. I just misspelled it on the title of this. Oops, sorry, the file. Anyways, that's some color on that, of some requested nature, no doubt. And that's just the framework itself for the name Dominic. And here we have the word, the name Edward, taken as a sequence, somewhat embossed with a red-blue theme going on. And here is, pardon my mispronunciation if so, but Gersimron, right there. Anyways, that's the framework of it. Very cool. And Jessica Michelle Eder. That's the framework of that. Notice these could get rather complicated. Now we're looking at these names as basically rational numbers, right? Or repeating integer sequences over base 36. This is the name Joseph. The catchy red and black coloration. Same name, but with blue and black and somewhat embossed. And here again, but with red and black. And here's Joshua. A very cool shape there. It's only slightly embossed. Here is Jules. There you go. And Jules in now red and green. And now red and magenta pinkish. And the name Kelly, and we can keep going here. Kimberly. We got, Lalo, cool name. Leslie, there we are, very pretty. And that's in more embossed there, and Leslie in some pinkish colors, and another name, very cool graph. And there we go. Actually, this is a sort of a splicing together of a couple names. There we are. And Mr. Beasley. Of course, the students that were saying, do your name. So it's funny, I had a little fun with them, but Mr. Beasley there. And that's what that looks like. Samantha. WB3. It's like my first letter and my last letter initial there with, and I'm Will Beasley, the third. So anyways, there you go. Sometimes I've used it to sign off on my art. At any rate. Okay, so there's the name graphs. And then you can do phrase graphs. Phrase graphs. And so that's always fun. Anyways, we get something like flowers. That's a picture of flowers there as far as Space 36 MRSGS systems are concerned. Or Mod 36. Flowers in a different color. Happy Father's Day. Made for a nice gift. Or part of the gift. And this is My Mom Rules. Yes. I'm not afraid to get corny here. Just the graph looks cool. And then Someone Rules. And someone's name, very artistically embellished. Some names. There we go. This is for a 1-year anniversary present for my now wife of 4 years. We've been together for quite some time now. Yes. Not quite 2 decades, but getting there. And just the words I love you, taken as a sequence of digits. The digit I, the digit L, the digit O, and so on, repeated. And so you can have some fun with these things as well. Yeah. And so we did those. Okay, yeah, just some word graphs here real quick. Because, you know, while you're at it, I wonder what the word fruit looks like. So this is my still life portrait of fruit. It's a bit unconventional, I know. But as far as the MRSGS with the mod 36 goes, this F-R-U-I-T are, well, they're digits, they're integers that are being graphed over the modulus of 36. And they are being repeated. So it's, yes, a very literal, so to speak, portrait of fruit. This is my landscape painting. With the word landscape, yes. This is the Mona Lisa. This is the Mona Lisa. I hope you can see the likeness here. Some of these are kind of funny. Okay, don't look, children. This is a nude painting, N-U-D-E, taken as a sequence of terms or digits, integers over mod 36. This is pain, because what art is made without pain, right? So, anyways, cliches of the sort. There's pain being portrayed right there in mod 36. This is the word portrait, hence a portrait in you know, of a very unspecific variety. in mod 36, it's portrait. And this is my self-portrait, or at least it's the self-portrait of all self-portraits, as in S-E-L-F-P-O-R. Yeah, anyways, get the idea. Taken as a sequence, graphed as such. This is, you know, the ever-popular cottages. You got paintings of those sorts, very popular. Anyways, my feelings on that aside, this is a graph of the C-O-T-T-A-G-E-S, shown right here. So, why buy all those cottage paintings when you could have the cottage painting right there? This is a portrait of Earth, well, the word Earth in mod 36. This is a female nude. There's that in art, very popular. These are flowers, we've seen that, variations. This is a male nude, sort of look. Mars, the word Mars, some cool colors. Mercury, so I thought why not do some planet names here. This is Van Gogh's Starry Night, as seen through the lens of MRSGS systems. So yeah, it's very, very similar. I think basically this is what Van Gogh meant to say. Not pretty sure about that. This is a portrait of just some trees. It's all the word trees anyway. Pretty cool, actually. This is Uranus. Moving on. Venus. It's quite a lovely simplicity here. V-E-N-U-S in base 36, or mod 36 in the MRSGS systems. And yeah, so that's the idea there. And I even went so far as to mess about with some ideas to have engraved on my wedding ring. The word union, base 36, also referencing my other research project with mathematics and musical rhythm. Same idea here. There. It's, you know, a portmanteau of my name and my wife's name, Laura. Yes. And will union origin. So anyways, I messed about with that. It turns out I went with something else entirely different for the engraving, but there you go. So the idea being here is that, well, you can do many wonderful things with these MRSGSs, including graphing numbers as represented in various, base numeral systems, base 10, binary, whatever. Usually a ternary and above, the graphs will be more interesting. Binary not being as much so. But that said, you can. At any rate, more recently, a rather popular YouTube channel called Numberphile came out with a video showing something rather very similar. So I figured I should finally share this, as I've been doing it for over several years at this point. And I have some more, more mathematically precise things to say about it, but I figured I might as well go ahead and share some of this now, seeing as how it's kind of coming out in from various other sources at this point in time. All right, well, so more of the depths on all of this later. Just wanted to share this with you more quickly than not. And yeah, there you go. Numbers graphed in MRSGSs.